This is a short presentation to introduce you to the concepts of correlation and regression. These methods can be used to test the relationship between data variables. Correlation measures the extent to which changes in the two sets of variables occur together in a linear manner, and regression gives a mathematical description of the relationship. So the information in this presentation refers to data sets where the relationship between the two sets of data is linear. Now, you've already covered linear regression in your core maths workshop on graphs. When the relationship between sets of data is linear, regression can be used to derive a formula. So here's an example of some data where the relationship between x and y is linear. And we can use linear regression to derive a formula which has the format y equals mx plus c, which describes the relationship between these two sets of data. So in this formula, m is the gradient or slope of the line, and c is the intercept on the y-axis. So essentially what we're doing here is mathematically putting a line of best fit to the data. A correlation coefficient, which we usually call R, measures the strength of that linear relationship between the two variables, and it ranges from -1 to +1. A positive value indicates that the two values change in the same direction, and a negative value indicates that one variable increases as the other one decreases. So the nearer that the value is to 1 or -1, the stronger the linear association between the two variables. If you draw it as a graph, there will be less scatter when the R value is close to 1. So let's have a look at some examples. This first example is an example of a positive correlation. So we've got our values x and y plotted, and we've got the linear regression line shown. So in this case we have a positive correlation. R equals 0.992, and that tells us that that's close to 1, so the correlation between x and y is good. Now I've also plotted on the graph the R squared value, which is 0.9849. And what this is quite a useful figure because I think it's quite easy to understand what the R squared value is telling us. It's telling us that 98.5% of the variance can be explained by the trend line. Okay, so this is an example of a good positive correlation between x and y. What does a negative correlation look like? So this is an example of a negative correlation. Again, we've got an R value which is close in this case to -1. It's minus 0.993. So we've got a good correlation between x and y, but in this case it's a negative correlation because as x increases, y decreases. The R squared value is 0.987, and so that's telling us that 98.7% of the variance can be explained by the trend line. Again, a good correlation. So let's have a think about what it would look like if we had data which was much more scattered than in these previous two examples. So here we have an example of a weak positive correlation. We can still put a regression line through the data, and we can see that there is a tendency for x and y to increase at the same time. However, the R value here is low, close to 0, and the R squared value tells us that only 33.4% of the variance can be explained by the trend line that we've shown. So this is an example of a weak positive correlation where the points are scattered. There's one final really important example that we need to look at, which is this one here. So again, we have a set of data showing how x and y change. We've put a regression line in here, and the correlation coefficient is close to 1. The R squared value tells us that 81% of the variation can be accounted for by the regression line. However, once you draw the data graphically, you can see immediately that it's not appropriate to try and put a linear regression line through this data, because the relationship actually isn't linear. And this sort of shape of data is quite typical of biological data, because it reaches either a plateau or a saturation point. And so although you can calculate a regression line and the correlation coefficient is large, we can't say that that regression line represents the data accurately. The choice of a linear regression in this case is clearly inappropriate. It would be better either to try and draw a line of best fit by hand through data like this, or to join adjacent dots. The key point here is that if the data isn't linear, then the choice of linear regression and therefore of the correlation coefficient is clearly inappropriate in trying to analyse the data.